In this program, we'll introduce the isomorphism theorem, and then we'll use it to answer these two questions, and to give you meaning for these very abstract expressions. To do this, we'll have to tie together ideas from several of the group theory units. In particular, the ideas of quotient group, homomorphism, image, kernel, and normal subgroup. But first, let's illustrate these ideas in the context of a group you're familiar with, the symmetry group of a square. Now, the square has 8 symmetries, the identity E, 3 rotations A, B, and C, and 4 reflections R, S, T, and U. Here's the Cayley table of this group of symmetries. In the pre-program work, you discovered something about the structure of this group. For this particular ordering of the elements along the borders, you can split up the body of the table into blocks. Each contains 2 different elements. For example, this block contains only the elements R and T, and this block contains only the elements E and B. Now, these 2 elements are special. They form a subgroup of S square. In fact, it's a normal subgroup, which is why we get blocking. The pairs of elements in the other blocks are not subgroups of S square. They are cosets of the normal subgroup EB. To construct these cosets from the subgroup, you pick any element of S square, say A, and compose it with E and with B in turn. This gives you the coset AC. And you get the same coset if you compose the element C with each of E and B. From the other elements of S square, you get 2 more cosets. R or T gives you the coset RT, and S or U gives you the coset SU. To simplify the table, I'm going to relabel the row headings in terms of cosets. The normal subgroup EB I'll call N. Then I'll label the next coset AN. That just means A times each element of N in turn. In the same way, I'll write the other cosets as Rn and Sn. And the subgroup itself is a coset. It's just E times each element of N in turn, so I'll call it En. So what happens if I replace each block in the body of the table by the label of the corresponding coset? This replaces the 8 by 8 table for S square by a new 4 by 4 table. The elements of this new group of order 4 are the 4 cosets. Here's the group operation, showing how the cosets combine. And the identity, that's En. This group of cosets is called the quotient group S square over EB. Its order is the quotient of the orders of S square and the subgroup. That's 8 over 2, so its order is 4. Now, up to isomorphism, there are just 2 groups of order 4, the Klein group and the cyclic group. The coloured blocks represent the different elements in these. So, which of these is our quotient group isomorphic to? Let's use the colours to compare the tables. If we look down the diagonal in the quotient group, we see that all the diagonal entries are the same. And that's also true of the Klein group. But the cyclic group has 2 different colours on its diagonal. So it follows that the quotient group S square over the normal subgroup EB is isomorphic to the Klein group.
We identified this quotient group by blocking the Cayley table. But in the rest of this programme, we'll be using homomorphisms to identify quotient groups. So let's begin by looking at what we've just done from a different point of view. we'll replace each of these cosets by a single letter. EN by capital E, AN by capital A, RN by capital R, and SN by capital S. Here's the completed Cayley table. When we blocked the Cayley table for S square, we clumped together these pairs of elements. And this gives a mapping from S square to the set EARS. For example, the elements E and B are mapped to E. A and C are mapped to A. R and T are mapped to R. And S and U are mapped to S. And EARS forms a group isomorphic to the Klein group. Now, obviously this mapping isn't 1-1, so it isn't an isomorphism. So what can we say about it? Well, it does preserve products. For example, the element C in S square is mapped to A, and T is mapped to R. But we can compose C with T to get S, and that's mapped to capital S. But in this group we can compose A with R to get capital S. So, to recap, taking products and then mapping gives us the same result as mapping and then taking products. And this is true no matter which elements of S square you start with. Such a mapping is called a homomorphism from S square to EARS. In general, if you take a group G with operation circle and a group H with operation star, then a mapping phi between them is a homomorphism if it preserves products. So, what does that mean? Well, if you take any two elements in the group G, say G1 and G2, phi maps them to their images in H. But we can compose G1 with G2 in G to get G1 circle G2, and then map that to its image. But in H, we can compose phi of G1 with phi of G2 to get phi of G1 star phi of G2. For phi to be a homomorphism, these must be equal for any two elements in the group G. The composite of the images must equal the image of the composite.
And here's the formal definition. If phi is a mapping from G circle to H star, then phi is a homomorphism if the image of the composite of any two elements in G is equal to the composite of their images in H. And now, let's see another example of a homomorphism. As you'll see, is just what we need to tackle one of the questions I asked at the beginning of the program.
For our group G, we'll take the non-zero complex numbers under multiplication. And for our group H, we'll take the non-zero real numbers under multiplication. Our mapping phi maps each complex number to its modulus, a real number. Let's check that phi is a homomorphism by seeing if it preserves products. Take any two complex numbers Z1 and Z2. Under phi, Z1 maps to mod Z1 and Z2 maps to mod Z2. The product of these two complex numbers is just the complex number Z1 times Z2, and that maps to its modulus. But the product of these two real numbers is just mod Z1 times mod Z2. For any complex numbers, these two expressions are always equal. Rewriting this in terms of phi, the image of the composite is equal to the composite of the images. So, phi is a homomorphism. Now, homomorphisms are mappings. So, what can we say about this mapping?
In this example, what set does phi map onto? Well, it's a set of all possible moduli. But the modulus of a complex number can't be negative, and we've already excluded 0. So phi maps onto R plus, the set of all positive real numbers. We call this set the image of phi. In general, the image of a homomorphism phi is a set of all elements of H that phi maps onto. We write it like this. And it turns out that the image is always a subgroup of H. So, in our complex numbers example, the image set of phi is a subgroup of positive real numbers. What else can we say about this mapping? The identity element of this group is the real number 1. Well, which complex numbers get mapped to it? That's just the set of complex numbers whose modulus is equal to 1. We call this set the kernel of the homomorphism. And in general, we define the kernel as follows. First, take the identity element in H. Then the kernel of the homomorphism is the set of all elements in G which map to the identity. And we write it like this. It turns out that the kernel is always a subgroup of G. Now, what's the kernel in our S-square example? Well, here, the identity element is the capital E. So, which elements from S-square get mapped to capital E? There are just 2, E and B. So the kernel of this homomorphism is the set EB, which we've already seen is a subgroup of S-square. But it's not just any subgroup of S-square, it's a normal subgroup. This is a general property of homomorphisms. For any homomorphism phi, its kernel is a normal subgroup. And in fact, it works the other way around too. Every normal subgroup is the kernel of some homomorphism. But which homomorphism?
Well, the homomorphism we're looking for maps G to the quotient group G over N, sending each element little g to the coset containing it. And the kernel of phi turns out to be just N, the normal subgroup. We're now in a position to state the theorem which will help us to answer the 2 questions that David asked at the beginning of the program. Remember, we found a homomorphism phi from S square to the group EARS. Now, this group is the image of the homomorphism, and the subgroup EB is its kernel. Also, we clump together the elements of S square into 4 cosets. These formed the quotient group S square over EB, and we found that it's isomorphic to the group EARS. But EB is the kernel of this homomorphism, and the group EARS is its image. So we found that the quotient group S square over the kernel of phi is isomorphic to the image of phi. And this is a special case of the isomorphism theorem. For any homomorphism phi between 2 groups G and H, the quotient group G over the kernel of phi is isomorphic to the image of phi. And now we can use this theorem to answer the 2 questions David asked at the beginning of the program.
First, how do we apply the isomorphism theorem to our complex numbers example? Here the group G is our group of non-zero complex numbers. Remember, the homomorphism phi maps each complex number to its modulus. The kernel is a set of complex numbers with modulus 1. And we've already worked out the image. it's the group of all possible moduli. That's just R plus under multiplication. So our quotient group is isomorphic to the positive real numbers. Now this all looks very abstract. What's it really telling us? Well, on the left, we have a quotient group whose elements are cosets of this normal subgroup. But what do these cosets look like in the complex plane? Let's start with the kernel. That's the set of complex numbers with modulus 1. They form a circle with radius 1. What about the other cosets? For example, what's the coset containing this element 2? It's obtained by multiplying all points in the kernel by 2, giving another circle. And what about the coset of this element, 3i? We get this circle. So the quotient group is a set of all concentric circles. And what's the isomorphism? Well, that maps each circle to a single number in R+, the radius of the circle. Now, how do we apply the isomorphism theorem to the other question I asked at the start of the program? Which group is the quotient group S tet over K4 isomorphic to? Well, our group G is the group S tet of symmetries of a tetrahedron. And our kernel is the Klein group K4. We need to find a homomorphism with this as its kernel, and then find the image of that homomorphism. But first, what are the elements of this group S tet?
Well, they're the symmetries of a tetrahedron, which you saw in an earlier program. First, there's the identity, E. Then there are 3 rotations about axes through midpoints of opposite sides. There's one axis here. I'll call this symmetry A. One axis here, I'll call this symmetry B. And another axis here. I'll call this symmetry C. There are other rotations. Each fixes one of the 4 vertices and rotates either through 1/3 of a turn or through 2/3 of a turn. Well, this gives all 12 direct symmetries of the tetrahedron. And then there are indirect symmetries, such as a reflection in this plane. And I get all 12 indirect symmetries by composing this reflection with each of the direct symmetries in turn. So the tetrahedron has 24 symmetries altogether. Now the 4 rotations, E, A, B and C, are special. They form a subgroup of S tet. But not just any subgroup, it's actually a normal subgroup and one that's isomorphic to K4.
So in S tet, I can think of K4 as the subgroup E, A, B, C. And because it's normal, I can use it as the kernel of some homomorphism phi. But what is phi? Well, certainly it must map the 4 elements of the kernel to the identity in the group M phi. What else can we say about the image of phi? Well, it's isomorphic to this quotient group. So its order must be the order of S tet, that's 24, divided by the order of K4, that's 4. So the order of M phi must be equal to 6. So the homomorphism must map the elements of S tet onto some group of order 6. But up to isomorphism, there are only 2 groups of order 6. There's the cyclic group and the permutation group S3. So does our homomorphism map the elements of S tet onto a cyclic group or a group like S3? Well, in fact, the image of phi is S3. And here's a geometric way of seeing just why.
We'll start with the tetrahedron and add in 3 coloured axes. A red one, a green one, and a blue one. The group of all permutations of these 3 axes is the group S3. So let's investigate how the symmetries of the tetrahedron permute these axes. Clearly, the identity symmetry in S-tet leaves the axes fixed. But so does the symmetry A, and the symmetry B, and C. So the 4 symmetries E, A, B, and C do all correspond to the identity permutation of the axes. How do the other symmetries of the tetrahedron permute the axes? Well, let's look at this rotation. This interchanges axes. And there are another 3 symmetries which permute the axes in the same way. Red goes to green, green goes to blue, and blue to red. But this symmetry gives a different permutation of the axes. It corresponds to another element of S3. And if we checked all 24 symmetries, they'd clump together into 6 blocks of 4. Symmetries in the same block correspond to the same permutation in S3, and symmetries in different blocks to different permutations in S3. So this mapping is the homomorphism, and its image is the whole of S3.
Right, now we've constructed a homomorphism phi with this as its kernel and with S3 as its image. So this quotient group is isomorphic to S3. Well, we've used the isomorphism theorem to answer both the questions we asked at the beginning of the program. The isomorphism theorem has given us a practical way of identifying quotient groups, and that's why it's so important.